To experience the full VR effect of this, what you're going to do is you can see on the screen here, it should mirror what you see on your phone. You've got three options. So the one, of course, we will walk through in just a second is how you actually view in VR mode. But the other two options, if for some reason VR mode just isn't working, those are your two non-VR mode options. And simply the difference is just kind of how you're going to navigate through the app. So they're both non-VR, but it just will depend on how you kind of touch and activate the scenes between those two. So again, if VR just isn't working, then you can back out at any time and you can switch modes on your phone. Now, let's get into setting up VR mode. So you're going to take your flip headset and you want to make sure it comes in the box all folded up. So you're going to undo your flip headset just like that. And you'll notice there's a clip here on the back. So this is what's going to go on your phone. So you're going to press VR mode on your phone. And then what you're going to notice is that you've now got this kind of binocular vision on your phone. And so you've got your two duplicate images. So what you want to do is take your headset and where that clip is, you're going to line it up right in the middle. And this may take just a second. For you, you might have to shift it just a little bit to the left, just a little bit to the right to ensure that you've got that 3D picture. So I'm going to give you guys just a second before we dive into the app to just have a play there, because then you can look at the phone and then come back and look at us.
Right, well, while you're getting your bearings, everyone, I want to acknowledge and thank Tyson for the wonderful outline interpreting going on. This is a key part of SciVR that it is for everyone. Space and science are for everyone. So I want to thank Tyson for joining us and his colleagues through this live stream event. Welcome all. Hopefully you've got your headset set up. You've got your clip attached. You're good to go. My name is Alan Duffy. I'm being joined by my astronomer colleague, Rebecca Allen, and we want to take you through a tour of the virtual cosmos. But before that, we're going to explore a very special initial scene. So let's click the VR mode, get your clips, get your bearings. You should see a dark landscape around you. There's lots of interesting icons. There's a sky above. What I want you to do is looking down at those icons and go all the way to your right. Hopefully you're sitting in a safe environment where you can start to move around, and go all the way to the acknowledgement of country. And then your little green icon should light up. Press the screen. And you will be transported into a very special location. Off to the left, you see a wonderful map of Australia, perhaps in a way you've never seen before. These are the language groups of the indigenous people, hundreds of diverse language groups across the country. You'll be able to click on a region and essentially get a little zoom in down below. This is showing the rich variety and heritage in this country, and it's on that point that I want to acknowledge the traditional custodians of the land from which I am joining you on this stream, the Wurundjeri people of the Kulin Nation. I want to pay my respects to the elders past, present, and emerging, and extend those respects to all Aboriginal and Torres Strait Islander people joining us. As Western literature is only beginning to understand in the last few years the incredible knowledge of the indigenous communities about space, the connections of land and sky, the patterns, the movement of the moon, and connections to tides and seasonal changes, even faithfully orally recording asteroid impacts from thousands of years ago. In all of these rich varieties of ways, the indigenous groups really were the first astronomers, and their extraordinary legacy of knowledge continues to this day. And I just want to extend those respects in particular for that exquisite knowledge. And really, we're just incredibly blessed to be in this country with such incredible legacies. Now, we are being joined nationally by many, many people. I want to give some shout outs. So thank you to Kingston in Tasmania. No, Kingston TS online out of Mind Beauty, the Discovery Science and Technology Centre in Victoria. Special shout out to Cindy of Gundagai Library, who handed out 48 cyber packs to people in lockdown, allowing them to be able to join. Thank you so much for that effort. In the background, you will have, of this stream, we have 8 volunteers from Osgrav, the Air Sea Centre of Excellence for Gravitational Wave Discovery, from ANU, Monash, University of Melbourne and Swinburne. They are busily answering your questions, which you can ask on Twitter or in the YouTube comments using the hashtag AskSciVR, so ask, SCIVR, and that will, those questions will either come through to me or Rebecca, and we'll try and answer it live, or our volunteers will be answering them for you. So get thinking about your questions and really just get asking to with you. You're joining us today in lockdown, so look, happy birthday. I hope, I promise, the next few birthdays will be more fun. I think this is a tough one, but you're joining us, so thank you for that. All right. So again, use the hashtag AskSciVR to ask your questions. And now, I think it's time for the tour to begin. Rebecca, where are we going to go?
So I believe, just, like any good journey, we have to start with where we know. So for our very first scene, we're going to make sure, you're backed out of acknowledgement of country, you're back in your home scene, and you're going to see, our lovely menu of scenes.
Oh, and sorry, hitting the home icon. Hitting that home icon.
Hit the home icon on your menu, your little green circle will light up. And what you're going to do to scroll over until your green circle is on top of solar system. Now, before we go into solar system, again, because we want this app to be accessible, there is actually, you're going to see on your menu a little microphone icon, a little speaker icon. And this is simply so whatever text is on the app will be read out to you. And so let's turn that off for now, just so you don't have that sound coming in as Alan and I are trying to talk. So as soon as you jump in that scene, you click once the green button lights up. You're going to want to tap on that speaker icon to turn off that auto sound. So Alan, I think we're going to jump into solar system, and let's explore.
That's good to me. All right. Wow, that's a big sun. That's what I've got right in my face. Hopefully everyone's very familiar with this this scene, this experience. It's not to scale. I always feel like I need to say that. The sun is absolutely massive, but let's make a familiar start. Let's go to the Earth. So you can either try to find the Earth in deepest space off to the right and click on it, or more easily, you can go to the menu down below and you see all the planets. You can see Earth. If you hover on with the green icon and you click, you will be transported to the Earth. And hopefully everyone is now seeing the moon go around. Oh my goodness, we've just been joined by Bright and Wangaratta. Thank you all for joining us from there. Hello, welcome to you're seeing Earth. I promise there's going to be more exciting fun things you'll see soon. So we're looking at Earth and you're seeing the moon go around, which is how we get the phases of the moon, because the sunlit side that we get to see on Earth is changing as it goes around in its orbit. It's a full moon when you get the sun and the Earth and the moon in a line, and it's a new moon when the moon comes between the sun and the Earth, because we can only see the shadowed rear of the moon. Now, this is a very special planet because there is liquid water on its surface, there's an atmosphere, and of course there's life. Now we're going to take a bit of a tour of some other interesting worlds. In particular, we're going to look at our twin sister planet, Venus. So, about the same size as the Earth. In fact, you can see, if you look to the left, it's obscuring the sun a little bit. There's a transit where it's passing between the Earth and the sun. So you can either click on it directly or, again, just use the menu, click. And we should now see a an orange kind of colored world. This is the surface of the planet. The actual planet itself has a tremendously thick, dense atmosphere, and it looks very beautifully bright white to us in the night sky, either early morning or at this point early evening, so the sun just sets, and close to where the sun has set, you'll see an incredibly bright star that doesn't twinkle. That's Venus, and it's such a beautiful white to us here on Earth because those clouds reflect the sunlight to us, and in fact, those clouds are made from sulfuric acid, and that's very reflective of sunlight. So it might look beautiful, and a lot of cultures associate it with romance and love. Couldn't be any further from the truth. Venus is a hellish world with acid rain and temperatures on the ground so high that that lead itself would melt. So very hot conditions. It's essentially a runaway greenhouse effect where the heat from the sun is being trapped by all those thick clouds. Now, it's interesting that it's had such a difference from us because, well, it's about the same size and it's almost the same distance to the sun as we are. We don't know why Venus has ended up so hostile for life and Earth so perfect. NASA is sending 2 missions just announced in the last month or two. The Da Vinci mission, which will be going to study the atmosphere, and Veritas, which will be scanning the surface and trying to understand, well, what happened in its history that made Venus so different to us. All right, now, the tour continues. Let's go down one of my favorite planets. Let's jump to Saturn. So if you can click Saturn down on the menu, hopefully you will now all have gasped because I did think it's quite cool. We have the rings of Saturn stretching overhead. Now, Saturn is a gas giant. It has these clouds, thousands of kilometers deep of clouds, and of course surrounding it are these beautiful rings. The rings are hundreds of thousands of kilometers across, but somewhere in the region of about a few tens of meters, maybe the size of a house in thickness. Just impossibly fine, thin structures that we can see from Earth. And this is a close-up view, essentially captured by Cassini and now brought into the VR app. Why we love the gas giants in particular, they're fascinating themselves, but the moons around them are even more so. And in particular, the moons of Jupiter and Saturn, some of them have the potential for life. We've now recently discovered liquid water under thick layers of ice. That water contains salts, organic materials, everything that you need to have life itself. We haven't found life yet, but we're very excited about that search. And again, there are missions from the European Space Agency and NASA intending to go to the gas giant moons to search for signs of life. Watch this space. We could find ET in our backyard. All right. Becca, I think there's one more special planet for us to take a tour of.
Thanks, Alan. So let's now step away from the gas giants, and on our final stop, let's go back to the terrestrial worlds, because you'll notice Alan purposefully skipped one of them on our little tour through the solar system. Let's now go to Mars. So if you'll go to your menu and click once on Mars, you're going to see a world that's much smaller than Saturn or Jupiter, but it's still very interesting to us. So when you're looking at the description of Mars, you're going to see some underlined words. And I want you to hover over Visit to Mars and click that. All right. Now we're getting a view of the surface of Mars and 2 very interesting and important pieces of equipment. This is the Perseverance rover, which landed on the red planet in February of this year. And if you scan slowly to the right, you're going to see the Ingenuity copter. This is the first rotary-powered machine to ever go to another world, and it has just completed its 12th test flight. And it's really important because while this little copter is small and you can press on it, hover over it, and give it a click to see it take off, while it's this very small size plane, we'll call it a plane, a little copter, drone. We don't have a word for these things yet. It's really actually important because this new technology is going to help things like that Perseverance rover, if you'll scroll back over, scout locations on the worlds that we explore, on the moons that we might explore. And the Perseverance rover, again, Alan was just talking about, well, where do we think there might be other life in our solar system? Well, we know Earth has it, but what about the other planets? And so we're having these missions like Perseverance to study the surface of these worlds, to understand more about, well, could there be life? And what's great about Perseverance is that it's landed in Jezero Crater, which we think is an ancient riverbed, not unlike some areas of Australia. And in fact, tying this back to Australia, one of the principal investigators on the Perseverance mission, Dr. Abigail Allwood, actually designed one of the instruments on this rover. And it's called the Pixel instrument. And what it does is it scans the landscape using a tool called spectroscopy to look for these organic molecules, which we think could make up the substance that creates life. Now, Perseverance hasn't been without its struggles. It's been a pretty successful mission, but it just tried its first attempt to drill down into the surface of Mars and collect a sample, which is really cool because then we can analyze it. Unfortunately, when it tried to pull that sample back up and then analyze it, it realized there was nothing there. So this is why it's actually really important that we have Ingenuity, because Ingenuity can fly along where we want Perseverance to go and say, you know what, maybe that's a better place to drill. So while Mars doesn't look very interesting at first glance, we're seeing all kinds of cool missions and science take place there. So stay tuned. But I think, Alan, maybe it's time for us to step away and leave.
Oh, well, I was about to say, we actually have our first question come through on the solar system. So we'll maybe answer these solar system questions before we leave, because we are about to travel from very, very far away. So Kate Neely has asked, if there is no water on Venus, how do you get acid rain? That's pretty good. So the idea is these thick clouds, just like any cloud, the acid, sulfuric acid is a liquid. It will condense and it will fall as rain, but it's so hot that rain never actually reaches the surface. So it's that hellish world that not even acid rain can reach the surface, but it is falling through the clouds at certain points. And indeed, certain regions of those clouds have temperatures and pressures that are actually pretty good and actually kind of similar to what we have here, which is why there are ideas and tentative signals that are kind of somewhat in dispute now that there may actually be the potential for life to be floating around in those clouds, certain layers of Venus, which permit life as we know it. Just as with Mars, there are certain regions perhaps below the soil protected from radiation that could actually still harbor life. So a lot of activity is underway to look for the places in our solar system where life may be able to survive. We're also being joined now by Fern Tree Gully, Adelaide, and Swan Hill. So welcome all. Thank you for joining. Make sure to use the hashtag AskSciVR. So that's Ask SCIVR on either Twitter or in the YouTube comment below. And we'll try to answer your questions in real time, or our amazing volunteers will get to it if we're just a bit too excited and we jump scenes, which we're about to do now.
That's right. So we're going to find our menu, and we're going to press the home screen button once again. And now we're going to journey pretty far away from our home.
Oh no, we've just had another question on Mars before we leave. I'm so sorry. I promise you, we can leave after this question, but this is one for you. Our Garfita Jossels has asked, is there water on Mars?
So this is actually, I think, a fantastic question. And at the end of the session, we might take a bit more of a deep dive into this. But the answer is yes, there is water on Mars, but not liquid flowing water. Now, this is what we think is the magic, kind of place where life began. But we do see ice water on Mars, and we do believe that either trapped in these kind of salt flows on the surface or deep below, so the poles, for instance, there could be reservoirs of liquid water, but it's so high in salt that we just don't know what would be able to live there because it's much, much more salty even than the oceans. And so there is water. It's a great question. And so that's the first question we think of. Is there water? But then also, what form is that water in? Because that's really important too when we're thinking about what life needs in terms of what we see on Earth to exist. So fantastic question. Glad you interrupted me there, Alan. And our wonderful volunteers who are also on Twitter, they might dive into these questions in more detail as well. So, all right. I think we've teased you enough. Now, let's head back to if you're not already on the home screen, please go back to the home screen. And now we're going to scroll to another one of our scenes. And I got to say, we don't like to have favorites here, but this one just might be my favorite. And remember, you might have to turn to access them. So we're going to go to All Sky View. So I want you to tap on All Sky View. And now you're going to see, I want to just take a second before we go into this. First of all, when you're looking at your menu, you'll see the 3 horizontal lines, or the hamburger, as it's called. If you press on this and hold it, you can actually drag your menu around, and that might be useful in the scene. So you can press on just tap once, and you'll notice that the text disappears completely. So if you just want a beautiful view to be immersed in, but then let's tap on it again to bring it back up, bring our menu back up. Now, we're going to also look over to the right at this cog wheel. And if we tap on that, it's going to bring up actually some extra things we can see. So for this scene, for us to navigate, let's look over, and I want to just click on a couple things. So let's turn on constellations, and let's turn on points of interest. So just tap with your green circle there, and then we're going to go back to the cog wheel and press that, close that menu down. Now, what are we looking at, first of all? I've given you an orientation. We're looking around, again, feel free, turn around. We're seeing our magnificent galaxy. So we've stepped back from our solar system, and now we're looking at the whole galaxy. And you can see these dust lanes, those are the dark bits. Then there's also these bright bits. So the reason we designed this scene is because we want you to appreciate that when we look out and study the universe, we use light, and we use all different kinds of light. And in fact, as Alan will explain later, we don't even have to use light all the time anymore. We've got some other tricks up our sleeve. But we're looking around in optical light. And so this is the light we see with our eyes. This is the light emitted by stars. And so we're going to go back and look at our constellations, which are going to kind of act as our map for this scene. And I want you guys, because we're mentioning stars and the light we see from stars. So let's use those constellations as a guide. And I want you to find the constellation Orion. And as a hint, you can find the constellations of the zodiac, so Cancer, Leo, kind of follow those down. If you can find Cancer, Orion should be near there. And it might be kind of more down towards your feet. So take a second and get oriented. All right. Now, actually, Orion's right below Gemini. Might be the easiest way to find it. Now, as we're looking at Orion, the thing I want you guys to see is I want you to slowly turn towards the right of Orion where he's got his sword hand up. And I want you to hover over, there's M1. Now, that's not a constellation. Let's click on M1.
I really should have done some more yoga. I'm really in pain here.
You guys didn't realize this is going to be an exercise class.
Yeah, big workout.
We like to keep the energy up. And speaking of energy, what you're looking at is called a supernova remnant. That means this is what's left after a star many times the mass of our sun explodes in a supernova. And so this is called the Crab Nebula. Now, I'll apologize now. We like to reuse words in astronomy, so you're going to hear nebula again. But what I wanted to show you about the scene is what we're looking at is actually a combination. This picture has been compiled from a combination of different types of light that allow us to see this full picture of what is going on. And so you can see all of this beautiful structure. And what that is that's the leftover layers of the star that have been exploded out and are being heated by things like X-rays, so much more energetic than our optical wavelengths. And at the very, very center of this supernova remnant is something called a pulsar. And this is what's left after that star explodes, the very, very small object. And you know what? You're looking at it, I don't see a pulsar there. I can't see anything. And that's because they're very, 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 very hard to see with optical wavelengths. They're so small. And so we actually have to use a different type of wavelength of light that Alan's going to take you through next. But before we do that, I just want to show you one more object that's linked to the life of stars, because that's kind of what we're exploring a bit more today. And we've got some incredible Australian astronomers who are working on pulsar research and these kind of stellar life cycles. So we're going to go into that a bit more. So tap on the Crab Nebula one more time, and that picture will disappear for you. So now we're going to just slide down, and we're going to actually go to another part of Orion. Just got to get the Crab Nebula out of the way there. So you'll see Orion's belt, and you'll see there M42. Let's tap on that. I just quickly wanted to show you this, because we just saw what happens at the end of a star's life. But what about where stars are born? So this is where the word nebula comes back. And you can actually see this, guys, if you have binoculars and it's a very, very clear night, you can find Orion and you can see this with your binoculars. So you can see this with a telescope. And so you can go out and you can see this. And this is also gas, vast clouds of hydrogen. And this is where stars are born. So we like to use nebula for what we see at the end of a star's life, but also at the beginning of a star's life. And so this is incredible because this whole process, we study this using light to understand more about how stars are formed and what happens when they die. But these are just single stars. Now, our galaxy is made up of many billions of stars, and that's just one galaxy. Our universe is made up of billions of galaxies. And something pretty cool happens when we get a lot of galaxies together. So, Alan, I might hand it over to you to navigate them to Abel.
Sure. All right. But before we leave the stars behind, we have a question. Rebecca, Talira Rose has asked, are there constellations associated with all the zodiac signs?
There are. And so constellations are our way of looking up and finding patterns in the stars we see. And they really can act as a map. And so the signs of the zodiac, they're incredible because the path that our sun takes through the sky is called the ecliptic. So for each month, it's in a different part of the zodiac. And so that's actually where that comes from, that's that arc of stars. And so we found a pattern there, and then we've given them names. Now these are, of course, were come up by people who were, Greek astronomers, and so old white guys. But many, many years before then, our indigenous astronomers were also looking up at the sky and finding patterns. And so this is what's incredible, is whether it's South America or the islands around Australia or Australia itself, for many centuries, indigenous astronomers have looked up to map out the stars, to link them to the processes that helped their way of life, whether it was agriculture or hunting. So these patterns are actually really important to our culture and to our history.
All right. Well, reminder to everyone, if you use the hashtag AskSciVR, so ask SCIVR, our team of volunteers will either answer your question directly there or pass it to us to ask and answer live. This will be a good one for you, Rebecca. Gracie Peterson has asked, how many constellations are there?
Oh gosh, I can't answer. I'm gonna say somewhere like 100. I should know this. I probably knew this a few years ago. And actually, you can find all kinds of cool maps. I do not know the answer of that off the top of my head.
I'm gonna lowball and go somewhere closer to 40, but that's just me trying to cover my bases.
I was gonna say I want to say 70. So.
I just thought I'd get you with that one, Rebecca, because I knew, like me, because that's the thing. As astronomers, we don't actually know much about constellations. Professional astronomers, we do. Yeah. Much of our time, we look deeper into the sky than the big picture structures that a constellation would have. And one of those deep sky structures I want you to now take a look at is Abell. So if you could look towards your feet, you should see a point of interest. It's really just directly in my belly, actually, just for me, but it's beside Pisces and near Fornax, really close to your feet. So it's called Abell 370. So if you click that, you will see a zoom-in picture, and that picture is now of not stars, but a cluster of galaxies. So dozens of enormous galaxies, the size of our Milky Way, if not larger, and they're all forming one ginormous superstructure called a galaxy cluster. Indeed, the galaxies buzz around like angry flies around a lamp. Just incredibly enormous structures. There is also something weird going on. I hope you can see that there's weird, almost snake-like structures just on the bottom left there of the image. So for me, it's upside down, but these are arcs. And what's happening is the enormous gravity of all of those galaxies and the galaxy cluster itself is distorting, like an optical illusion, the background universe. So as the light from the universe behind this galaxy cluster, from our point of view, streams towards pictures of galaxies, essentially, are being distorted and twisted and formed into these arcs by gravitational lensing. This is something Einstein predicted. The amount of lensing we see, all of those arcs, and by the way, there's about a dozen, give or take. They're super tricky to see them all, but lots and lots of little arcs in there as the background images of galaxies are sheared and twisted and distorted like a fun house, mirror illusions. Now, using those arcs, you can figure out just where the gravity, and that is to say the mass of that galaxy cluster is, and we see that in fact it is filled with enormous amounts of material that is otherwise invisible. This is called dark matter. In fact, about 5 times more dark matter than every atom we can see combined in our universe. So there's just a lot of dark matter out there, and this cluster has a same amount, so about 5 times more dark matter than all of the normal kinds of atoms combined. So huge amounts of this mysterious stuff. We don't know what it is, but Australia is leading the effort to find it with the ARC Centre of Excellence for Dark Matter Particle Physics, of which I am a part, led by UniMel's Professor Elisabetta Barberio, is trying to find out the nature of dark matter. Hopefully next year we might be able to tell you more about what that dark matter is. Could be particles, could be primordial black holes. There's just so many exciting potential ideas out there, and we're trying to figure it out. But it all started with astronomy through efforts like this, where essentially the universe revealed the presence of an otherwise invisible structure by its gravity, and in this particular instance, gravitational lensing.
Now, Alan, you just gone through that and you don't have a question.
Well, Dan, well, oh, were you gonna? I was gonna ask you the questions again. Okay,
That's fine. Go ahead.
Okay, Dana O'Neill has asked, "What are stars made out of?"
Ooh, fantastic question. This is such a fundamental question. So stars are mostly made out of hydrogen, and that's because hydrogen is the most abundant element in our universe. And this is part of something which very closely links to what Alan was just talking about with dark matter. It's called cosmology. And that's where we really try to define the history of our whole universe. And so we know very early on in the history of our universe, when all the preliminary elements were made, that hydrogen was the most abundant. And you know why stars are important? We actually wouldn't have the other elements without stars, because it's within their cores where there's so much pressure that atoms are actually mushed together and fused and build up heavier and heavier elements. So fantastic question. So the very first stars were basically mostly hydrogen. And then from then on, we built up the heavier and heavier elements. And stars like our sun will actually have many different types of elements in their outer atmospheres and their outer layers. And that's how we get planets, because what was left over from when stars forms the rest of everything else. So little did you know it, but you asked a very fundamental question. Thank you.
Now, Cindy Smith has asked, "What is our universe's most distant star? And if you could travel the speed of light, how long would it take to get there?" Look, I might jump on this very quickly. It's very hard to see an individual star, even with the Hubble Space Telescope, even if the image is boosted by gravitational lensing, which acts like another super-powered kind of telescope. So we're not sure about individual stars, but we think that the first stars were, as Rebecca said, made from hydrogen and helium. They were enormous, hundreds of times larger, maybe 1,000 times more massive than our own sun. They were incredibly bright, that those might have been visible, and a new telescope, JWST, perhaps might actually directly see those very, very first stars. So they would be formed in the first few 100 million years after the Big Bang. That would mean that they would be the age of the universe ago. So essentially, 13.5 billion years ago. Because the universe has expanded, they're not 13 billion light years away, which is the distance the light travels in a year, but actually about closer to, I think, 44 billion light years. And if you try to travel there at the speed of light, okay, it might take you the 44 billion years. It probably take you longer because the universe is expanding. And either way, by the time you got there, the star itself would have ended because it only lived for about 1 million years. So the very most distant stars, we're seeing the echo of what they used to be. The light has traveled for billions of years to reach us. The star itself that formed it has since exploded. So what we're seeing is the light echo, what used to be there coming towards us. So, all right, lots of constellation questions. I'm going to have to leave those. I will just say very quickly to Rebecca, oh my goodness, in the interest of time, Jacqueline Carberry has asked, why do you have to wear a special suit in space and not just like a helmet with an air tank?
This is a good question. So we're used to living in the protective layer of our atmosphere on Earth, and Earth just provides protection in so many different ways. And again, I'm happy for our volunteers to delve into this a bit more. But the key components are, we have a magnetic field and we have an atmosphere. And these act to shield us, but also to regulate the temperature. And this is why we have the Goldilocks and the three bears of Venus is too hot, too much atmosphere, too thick. Earth just right. Mars, not a lot of magnetic field, not a lot of atmosphere, probably pretty cold. Okay, and it just the temperature fluctuates a lot. You don't have that stability. So actually, when we leave Earth's protective cocoon, we're now exposed to things like radiation and also this very cold temperature, many degrees, less than 0 degrees Celsius, out in space. So it's not just about the lack of oxygen, it's about the lack of anything to protect us and to keep that stable temperature.
All right. Now, we are going to do just a very brief little tour of the rest of All Sky, and then we're going to have to do some other scenes because we want you to get a bit of a taste of everything that's in the app, but obviously you can take your own tours later. Please hit the hamburger if it's not open for you on your menu, so you get this wiggly line, because I want to now show you what the universe looks like if you had different kinds of eyes. So far we're looking at optical. So now you've got this wiggly line in front of you. This is all the different kinds of light. It's known as the electromagnetic spectrum. It goes from long wavelength, low frequency, low energy light on the left, like radio, to high frequency, short wavelength, high energy light on the right, like UV, X-ray, and even gamma rays. Okay, now what I want us to do is to select the long wavelength, so that's at the very far left, and I want you to look at radio wavelength. So click radio, and hopefully things have changed for you. Look how different the sky now looks if you have radio eyes versus the optical or the normal visible light that we've seen before. In particular, on this radio map, what we're seeing now is the glowing gas, so not stars, but the gas that builds stars, the hydrogen that Rebecca mentioned, that's floating around in the galaxy itself, and it's shining in radio wavelengths. It's got a similar distribution, but it's subtly different. I want to now look to, that's very cold gas, but you can also look at very energetic kinds of events, super high temperature events as well with radio. And a beautiful example is right in the middle of our Milky Way, called Sagittarius A star. It's the little yellow dot. You can see it's glowing a little bright there. Well, click the button and we'll zoom in now. And we're zooming in to a picture that was captured by Meerkat. This is the South African-based square kilometer array pathfinder. Essentially, it's a ginormous telescope that looked deep into the heart of our galaxy and revealed the intense gas and swirling magnetic fields and all this wonderful physics going on at the very center, all around a supermassive black hole. I suspect we'll get some questions about black holes, so maybe I won't answer too much at this point, but enormous amounts of gravity pulls in material, swirls it around, it heats up, and it does interesting kinds of physics that we are seeing glowing brightly there. So again, just to remind, and just all the little sweeping filaments, and almost like little mini tornadoes going on. These are swirling magnetic fields across space itself. So just an amazing picture that is less than a year old, I think. This is super new result. Okay, so we can also look at slightly different kinds of wavelengths of light. So we talked about radio. Maybe is there one more radio image we can actually show? Because I really love it. Is it the gleam? Oh, it is. If you could just click gleam, we don't have time for this, but I love it so much. This is a beautiful image from the Work Wide Field Array, MWA, based in Western Australia. And again, look how different the galaxy looks. All these glowing dots, and in particular, if you can go, yes, just there, Centaurus. So if you go up above the plane of our galaxy, in my case, it's towards my right shoulder, and there you see this glowing bright object. This is really cool. Remember what that looks like. Go down to the color, the light bar. In fact, maybe even let's be fancy, guys. Let's drag our menu up. All right, so here, remember how we do that? We hold the trigger button on the little burger, holding your finger on the menu, and we'll pull it up, which I can do, but Carl doesn't seem to be able to. Hopefully you're all able to pull this up towards Centaurus, so you can keep it in frame. All good. If Carl can't, that's fine. What we're going to do is we're going to click optical. So we remember what Centaurus looks like in radio, and we're going to click optical. I'm going to look back up at this familiar image of Milky Way, and Centaurus has gone. You've got the little labeling to tell you where it is. in optical, our normal visible light is completely just unnoticeable, but in the radio, in this NWA image, it was glowing brightly. And that, again, was a supermassive black hole that was feeding and that was throwing out material into jets and up and below the galaxy. So we're actually seeing a feeding supermassive black hole through radio. And Australia has done some wonderful work with radio. We've got the Square Kilometre Array that's coming online. Construction has just begun. The biggest telescope ever imagined, quite frankly. Half of it in Australia, half of it across Africa. A wonderful project, and Australia will be at the frontier of science for many years to come, exploring things like these supermassive black holes, but also the pulsars that Rebecca has mentioned before. Rebecca, do we want to just jump straight in to making a pulsar, or did you want to do anything?
Yeah, that's what I was going to say. So, please, guys, there's other wavelengths of light, especially the high energy ones. X-ray are just as interesting. Come back and explore those in your own time and do Alan's trick of jumping between optical and the other wavelengths to really appreciate why we need these other wavelengths to build up the picture of our universe.
Oh, now, by the way, we're getting lots of oh, wow, that blew my mind. M87 is very cool. And yeah, they are very cool. And Gracie Peterson has asked what makes the colors in the galaxy. We have our visible colors, red and blues, of course. Blue light is shorter wavelength than red and higher energy. Even higher energy, shorter wavelength is ultraviolet. That's actually such energetic light that we have to protect ourselves with sunscreen. Once you go either bluer than blue, so into ultraviolet, or redder than red, and that's pushing you into longer wavelengths like infrared, which we can't see, but you can feel the warmth of say, sunlight on your skin. Once you get to those points, it's kind of up to us what we make the picture look like. The telescope is seeing radio wavelengths, and we try to use colors that make sense for our eyes to look at that picture. Computers can handle it, our eyes can't, so we have to choose a color that makes the most sense, and NASA in particular does great work with choosing colors that make physics sense and also look beautiful. But all the colors in the galaxy, in visible light at least, is, well, star shining gas, blocking that light and other things going on. And the other wavelengths, it's all sorts of other physics going on.
Absolutely.
That's why it's so cool. All right, now let's, had to jump in there. All right.
That's all right, you guys. Fantastic questions. Really appreciate it being interactive because we're so sad we can't be there with you in person. But you know what? This is the beauty of SciVR, is you can explore the universe without even leaving your office chair or your couch, wherever you guys are, your library. Hopefully some of you are in person. So we're going to go and we're going to click on our home screen on our menu one more time. Well, not one more, but another time.
Another time. There might be one more. We only have 12 minutes left.
Okay. So we're going to jump in. We're going to jump into Star Lab. I'm going to keep this really short because I want Alan to get to show you then as well LIGO. So let's jump into Star Lab. And some of the features of this you're going to have to explore in your own time because we just made this app way too cool. But we wanted to create Star Lab because we want you to understand how do we get to these cool things like pulsars and what are these different objects. So you're going to look around and you have now in front of you a whole console that you can look at. And so you're going to see three main objects. Transients, you're going to see stellar remnants. Oh, sorry, I was about to say, I thought we put black hole special, but they're in stellar remnants. But we have our transients, and transient is a fancy word for it's there and then it's not. It's there and then it's not. But it turns out this is actually some of the most interesting science because this is where we see like the supernova explosions or little stars, which are much less massive than our sun, called dwarfs, can actually belch out solar flares much more powerful than what our sun can do. So they're called stellar flares. And so I won't click on that one because I want to save some time. But what you can do with any of these objects, we're going to actually shift and we're going to go over. So flare star, much less massive than our sun, and it's an actual star. But if we go over to stellar remnants, you'll see white dwarf. And that's what happens when a star like our sun dies. It goes through all of its fuel until it gets to oxygen, blows out those outer layers. But let's go through the journey of a star about 10 times the mass of our sun. So I want you to click on neutron star. So tap that, and you're going to look up above your console. And you're going to see this beautiful star that Mark, our developer, built. It's so gorgeous. Of course, they're purple. Let's be real. But what I want you to do is hover your green circle over that and tap it. Whoa! Oh my gosh. We've just evolved a star, something that takes at least millions of years to do with one click, with one tap. Now, this is our pulsar growing through the phases of its life. It's actually burned through all of its material, and that's when we say it's hydrogen fuel, building heavier and heavier elements. Uh-oh, we're at iron. Can't burn anymore. Let's now tap one more time and see what happens. Boom! Supernova. Now at the core, we have a star. So what's happened is all of this matter has condensed down further, and that's condensed the magnetic field. And so it just powers up this magnetic field, and any matter that happens to be right around that area gets accelerated close to the speed of light, blasting out radio jets. And guess what? Here in Australia, using things like the Parkes radio telescope, we can detect those pulses of radio energy and see something which would essentially be invisible, but is actually very energetic and is very strong. And pulsars, they represent this extreme form of matter, so they're very important for us to study. Now, I won't go into too much more depth because I want Alan to now jump in and show you what happens when a star goes beyond a pulsar, and talk about some funky stuff that happens with gravity.
All right, that's right. Everyone's favorite extreme form of matter. Let's go back down to the stellar remnants. And you may have missed it, there's actually a third stage, even smaller, even denser than a neutron star, and that is a black hole. So there's a little black dot, so click that. And if you go look back up, you see we start again, a massive, massive star. We click it, and it ages and bloats and swells up. And then we will click it again to explode, and it explodes, leaving behind, well, it doesn't seem to have left behind anything, right? Interesting. There's no light that I can see. It must be fine. I should go wander over there. Just before you do that, let's just have a little check. We've got a neutrino cannon. Scroll down to the right. We're going to see if anything's actually there. So this is, neutrinos are kind of a particle. They can fly through solid matter, but they're pulled by gravity. So let's just have a look. Let's just click the red trigger, and it fires a blast of particles out. And oh, look, they seem to be being pulled around by something out there, something with enormous amount of gravity pulling it around like a planet is pulled around the sun through that gravity. That is the black hole. So something with mass, because it has gravity, but it's indeed so much gravity that not even light can escape it. That's the black bit of the black hole. We have, essentially we're able to see it through its effects on other material, the gravity, and I've talked about in other wavelengths of light how it can glow brightly as it's feeding and blasting out material, but we can see it directly through its gravity, and this is one of the most extraordinary recent inventions in science, and that is the gravitational wave detectors. So let's go.
I was going to say, that's just one black hole. That's just one pulsar, but let's show them what happens when two black holes get together and love each other very much.
That's right. Family show. All right, let's go to the home icon, hitting home, and we'll, in the last 5 minutes, we're going to now jump to LIGO. So go off to the right, and again, you can ask your questions, ask SciVR, SCIVR, on Twitter or the YouTube comments below, and our volunteers will answer them now if we don't get a chance to in the last few minutes. So if you click LIGO and you go to a very special room, this is a gravitational wave detector. It's basically our version of that. This is two ginormous arms, 4 kilometers long, that we're going to shine a laser back and forth. We're going to make the most precise ruler that's ever been created. So hit the green button, and you can see the two lasers turn on. And now what we're going to do is have two black holes whose gravity will pull them together. They will collide. They will emit gravitational waves. These are the stretching of space-time itself, predicted by Einstein, and it is going to stretch out the detector, and we will see, hopefully, how that works. Now, let's find your black hole. Let's do the black hole merger. So click that button. Doesn't look like anything's happening, except, oh, look at the laser. Something's shining on the surface. There's an interesting pattern. I wonder what's causing that. Let's look up to the right, and we can see there are two black holes swirling around. Carl has put in this beautiful image of the swirling of space-time itself. That is what's stretching and straining the entire Earth. In fact, as it passes, these gravitational waves pass through us, it's stretching and straining our detectors. The two 4-kilometer arms are stretched slightly more distant to one than the other. It means that the light from the lasers, when it's exactly 4 kilometers, they both cancel out and you get blackness on the screen. And when one is stretched slightly bigger than the other, a little bit of light survives, and we can pick that up. And that stretching is what the gravitational waves are doing as they pass through the Earth, caused by these colliding black holes. Now, you can run through lots of different ones. The whole shaking of the Earth, and indeed the detector, has stopped because the black holes have collided together and formed one bigger black hole. This is a series of detectors now around the world that do this. Essentially, the amount that we're seeing shift is about the difference between here, the planet Earth, and Jupiter stretches by about the distance of a width of a human hair. Seems an impossible amount, except these detectors are so sensitive, they can measure the difference between here to the nearest star moving by about the width of a human hair. So an impossibly fine ruler, basically. Making all that technology possible, some wonderful Australian efforts. We have the mirrors that reflect that laser back and forth, developed by the CSIRO. The work continues on improving those mirrors by ANU and at the University of Adelaide. And indeed, Uni Adelaide is now trying to improve the lasers themselves. At UWA, the suspension systems that hold the mirrors have been developed, as well as fast processing pipeline called SPHERE that helps us analyze gravitational wave signals. At Monash University, they've developed another code called Bilby that's used worldwide to turn gravitational waves into actual, astrophysics, what we know about those black holes and other things that collide. And Swinburne does that, as well as use the Oscar supercomputer to process the gravitational wave signals, as well as also find pulsars. Huge amount of work. It's a national effort. It's all under the auspices of Osgrav. Go Australia. All right, good. Now, we're very much running out of time. Let's quickly jump back to the home screen, because I just want to remind you just to look at some of the other scenes, like the Baker Room, which was a photo pre-COVID when we were actually doing real-time discovery, lots of astronomers in a room together doing great work. It was amazing. You're going to have to look at that in your own time, because we have run out of time. Gracie Pearson has asked, are aliens real? Aliens are definitely out there. There are billions of Earth-like worlds in our galaxy alone with the potential for hosting life. It seems incredible to me that they are devoid of life, but I don't think aliens have come here. Good. All right. That's it. Any other questions? Keep asking them. Our volunteers will do their best to answer. Huge thanks to Megan and Tyson, our incredible Auslan interpreters. Thank you for your work. For all of our volunteers answering the questions, Hannah and Lucy from University of Melbourne, Andrew from Swinburne, Reinhold from Monash, Sean, Disha, Anushka, and Johannes from ANU. Thank you all for your efforts. Make sure you go to SciVR.com.au, click the link to the survey to give us your feedback. I want to thank, huge thanks to Inspiring Australia for making the National Science Week possible, giving us the grant to run this event, to send you these cool headsets out. Thanks to them, thanks to Swinburne, and of course, thanks to the ARC Centre of Excellence for Gravitational Wave Discovery, Osgrav, for the incredible support, tremendous support. my thanks hugely to the team behind the scenes. We have Carl Knox, Mark Mars, who basically developed the art, developed the app that you're seeing and you're enjoying. James Josephides was involved in some of the artwork. Thank you for that. Jackie Bondell, amazing outreach efforts across Ostrava and even the Dark Matter Center. And I have to say, superstar Lisa Fordley, thank you so much for all of your work in making this possible. It's like so many moving parts. You've done an amazing job as ever. Huge thanks to my colleague, Becca Allen, for wonderful co-hosting this year and indeed all of the other years. Once again, go to scivr.com.au, click the link for the survey. We want to hear what you thought, and just a huge thanks all round. Have I missed anything? I think that's everything.
It's certainly not been a traditional science week, but we're so excited that you guys across the country have gotten to take a tour of the universe with us. And again, keep exploring the app, keep exploring those scenes. And it's so great to get to share the wonderful astronomy research that we're doing in Australia with you guys. So take care.
Take care. And again, Lillian, happy 7th birthday. I hope your 8th is out of lockdown. Stay safe. Stay safe all, and enjoy the rest of your science week.